Okay, and it's exactly on the hour.
Yeah. Well, we're very pleased today to welcome Rob Kirby, who's going to continue his talk on trisections.
Okay, so let's see. I should assume that all of our. Oh, I know what I want to do. I have a question for you to start with. Where does who first coined the phrase "swallow follow"? When you have a knot, and then you have a knot, the trefoil. Here's the trefoil, as we always, and then you take a little bit of it and you tie another little knot in there, and then you push that knot all the way around and come back. The swallow follow construction. So who coined that phrase? Anybody remember?
Never heard it before.
No, nor have I.
Never heard it before.
I mean, it's in Fox's Quick Trip, but
oh, maybe Fox did in the Quick Trip. But Colin, you say you never heard the phrase
Never heard that expression.
Follow?
No.
You just get back where you started, don't you?
Yeah, but it's
yes, but this is an interesting isotopic concordance or something or other of the knot. Okay, I just wondered if anybody had a reference for where that.
In his book from 1974. Where did you get it, Dale?
Dale?
What?
You use it in your book, Swallow.
Yeah, where does swallow follow come from?
I think it comes from Conway's proof that knots don't have inverses. You take a sum of two knots, and then you take a tube that follows one and swallows the other.
Yeah.
And
that was a beautiful proof. It's on the internet somewhere, I remember.
It is, yeah.
So it may be Conway. It would be like Conway to come up with a name like swallow follow.
yeah, it's a sort of
Probably,
yeah.
Yeah. Okay. Well, that's just an aside. Okay. So now, just to remind you, a trisection. So a trisection of a four manifold X, which is always smooth, connected, closed, compact. A nice four manifold. Trisection of that. Well, I'll just briefly say what the construction was, and if you are new, why this won't help much. But anyway, we constructed a map to the disk. This is B2. We constructed a map. This is somewhat analogous to complex surfaces, and you map them down to CP1, and you get elliptic surfaces and so on. This is kind of this map down is called a Morse 2 function. And this is work I did with Dave Gay. I should always remember him, put his name in here. And see, it is a Morse 2 function. And then it turns out that you can draw the basic pre-image of this point, center point, is a surface of genus G. So over the point lies a surface. And then as you draw a ray out, I don't know why my pen changes to an eraser without my asking it to. Anyway, if you look at a ray, then over that ray, there's just a point here, which is really the mid. So over that ray is a handle body that's sigma G bounds. So over this is a handle. I'll just say a handle body H over that ray. And so as you go from the surface, you fill in a 2-disc, you fill in another 2-disc, another and another, and finally you fill in a 3-ball, and this is the center point of that 3-ball. So over that you have a solid handle body. And then over another, this is true over all the rays, but I want to single out 3 rays. And these are 3 different handle bodies. And we tend to call so you're in this central surface, sigma G, you see, so here's the surface of genus whatever, genus G. And in there, you see one set of curves, which we'll call the alphas. And they're usually in red, just by tradition. And then you see, this is the reds, this is the alphas there. And then over another slice, you see the betas, which is in blue. And maybe they're nice. You can arrange them to be nice if you wish by handle slides. And then the other possibility is the greens, the gammas. And now they're very complicated. They're whatever, they wander all over the place in general. You know, maybe one of them looks like that, and maybe another. I don't know. They're complicated. However, it could be that one of them looks like this. Comes along, it goes under, comes out here, and crosses the blue and the red and comes back. This thing all by itself is CP2. In other words, if you think of this torus, just this torus, and you write it as a square, then you've got, that's gamma, and then this is, say, the red alpha, and then this is the blue, which is beta. And so then if you think of those 3 curves, meridian, longitude, and a 1-1 curve, those curves would give you a trisection of CP2. And if you remember CP2, well, this is an example. So in the case of CP2, you can make it from 3 4-balls, and each one of these is, I didn't mention this last time, I think. Maybe I should get into it now, but each of these, above each one of these sectors is the 4-ball. And you can build CP2 with 3 4-balls. Or, anyway, that's it. So a trisection is something that looks like this, where you have a collection of alphas, a collection of betas, and a collection of gammas. And so they're on the surface, they're this collection of either the red curves, the blue curves, or the green curves, and they will determine a 4-manifold, and every 4-manifold has such a trisection. And the trisection is unique up to stabilization and handle slides. And by handle slides, I mean you can slide alphas over alphas, and or betas over betas, or gammas over gammas, and that won't change. That doesn't change these handle bodies. They just give you different cut systems, but it doesn't change the handle body, and therefore it doesn't change the 4-manifold. And by stabilization, I mean the following. This, you can stabilize by taking the 4-sphere there's the simplest stabilization of the 4-sphere is just to project it down to the 2-ball by taking the 4-sphere and flattening it to the 4-ball, just by taking the upper hemisphere and the bottom hemisphere and flattening them out to the 4-ball, and then projecting the 4-ball onto the 2-ball. So that will give you a trisection that looks like taking an orange and dividing it into, taking the peel off and dividing it into 3 equal sort of triangular sections. That's the analogy. Well, that's the trivial trisection of the 4-ball. But you can also take the easiest non-trivial trisection of it, and then that's what I mean. Then you just connect some with that, and that's what's meant by a stabilization. So anyway, this is all in the paper that Dave and I wrote some time back. So now what I want to do today is go from this to a group trisection. So notice the first thing you can do with this picture is to, well, I'll leave it up here, and is to first apply the pi1 functor. In other words, just take pi1 of all these things. So, for example, you have pi1 of the 4 manifold. You have pi1 of the surface. And then you have pi1 of these handle bodies, 3 handle bodies. And you can put them together into a cube. So now now I'm going to erase some of this in order to not give up this picture of the trisection. So we're applying the pi1 functor. And so we can start off with pi1 of the central surface. There's a base point, but let me ignore the base point. And so this is, the fundamental group. It's generated by the alphas and betas with the commutator is the one relation. And now, if you have the pi1 of the central surface and you map to the handle body, well, the handle body, it collapses to a wedge of circles, and it's a wedge of G circles. So if you do that collapse, you have an epimorphism to the free group with G generators. You're just collapsing down to the wedge of circles. Pi1 of that is that. But you can do that for the reds, the alphas. It is. Well, no, I didn't make enough room. So I guess I'm going to erase this. You've got that in mind, I hope. And then you can do it for the gamma. So this is sort of the alpha version, the beta version, and then you can map to that's both are all epimorphisms, and this is the gamma version. So you have these 3 epimorphisms. Well, what's the next thing you know from this trisection? Well, you know that if you look at that 3 manifold, in other words, if you put H, this is really H alpha, and this is H beta for that handle body. Then if you put H alpha and H beta together, you happen to know that H alpha union H beta is equal to a connect sum, actually, of K copies of S1 cross S2. So why do you know that? Well, I said that last time, but I didn't review it. This is true. Well, this came out of the proof of the existence of a trisection. It came out of that. Here was the case for, I wrote down B4, that was for CP2. But in general, so let me erase that, because in general, what this is a connect sum of S1 cross B3, and it's K copies. K is not G. For the case of CP2, K was 0, but this was the solid torus. The handle body was. So without going, I can go back to this later if you want to know why that's true. But then I'd have to go back into the trisection construction. So what that tells you is that if you put two of these together, for example, the alpha and the beta, then the push out down here is a free group of rank K. That's just von Kampen's theorem. It's just von Kampen's theorem. So, but all the push outs are that. So you have another push out to another FK and another push out these are epimorphisms also. Another push out to FK. So it's kind of a beginning. You've almost got a cube here. Well, then the final push out here goes to pi 1 of the 4 manifold. So this is what's called a group trisection. It's just what you get by applying the fundamental group to this trisection of the 4 manifold. So let me stop and ask for questions. Are you all? Yeah, many questions.
If you want to ask Rob a question, you can either send it via chat or unmute yourself. I think you're allowed to unmute yourself. So.
Yeah. Okay. Well, anyway, always interrupt with questions. So the interesting theorem, now this is a theorem of Aaron Abrams. A student of Andrew Casson back around 20 years ago, and also Dave Gay and I. And so what's the theorem? The theorem is that there exists a bisection, a one-to-one correspondence between the set of all of the 4 manifolds above, again, closed, compact, connected, orientable. I didn't say orientable before. That's worth putting in because we haven't worked out anything for the non-orientable case. So a bisection between those guys and group trisections. Group, so this is group.
Did you mean a bijection?
A bijection. What did I say?
A bisection.
I meant a bijection, yes. A one-to-one correspondence, a bijection between the 4 manifolds and group trisections. And there's a stabilization operation, so up to stabilization. And the stabilization is just changing this by taking the group trisection for the stabilization of the force sphere, the first non-trivial trisection of the force sphere. So the stabilization doesn't matter too much. So it turns out then that, so think about this theorem, that there's a bijection between 4 manifolds and group trisections. Well, what group trisections? The group, of course, has to be finitely presented. So those are the groups of 4 manifolds. Every finitely presented group is the fundamental group of a 4 manifold, oriented nice 4 manifold. So we're talking about those groups, and then the class of trisections of those groups is essentially the same as 4 manifolds, trisected 4 manifolds. Well, four manifolds. Not trisection four, but just four manifolds. And so that's the theorem. And what it means, well, here's one sort of corollary of that, or just a comment about it, is that pi1 of, even if pi1 of x is trivial, the trivial group has interesting group trisections. And how many interesting group trisections does the trivial group have? As many as the smooth structures on simply connected four manifolds. So if you take a four manifold, a simply connected four manifold that has countably many smooth structures, for example, K3, the complex surface K3 has at least Z plus Z, at least a two parameter family of different exotic smooth structures. And those exotic smooth structures have to appear among the group trisections of the trivial group. So a group trisection of a group has a lot of information in it beyond just the fundamental group itself. A lot more. A lot more. So this is, by the way, a group trisection is analogous to in dimension 3 to just a square of it would be called a group bisection, analogous to a Hagar splitting of a three manifold. But if the fundamental group is trivial, then there are not any exotic bisections of the trivial group. But for group trisections, there are all sorts of them. So how do we prove this? Well, it turns out to be practically trivial to prove. So how does the proof go? Well, I'm gonna erase some more so that I can keep this group trisection on this one page. I'm gonna give you, I don't know, maybe you all hate this, that I keep erasing stuff, but we can certainly erase, well, I could erase the definition of the stabilization. I can erase that theorem. And I could erase the authors. All right, so working up then in that corner, I want to take a group trisection and build a four manifold. If we can go, going one way, if you start with the four manifold, the arrow to group trisections, you just apply the fundamental group. So that arrow is easy. Now what we want to do is construct the arrow backwards, where we take a group trisection and construct the four manifold. So how do you do that? Well, we start with the surface sigma g, and you might as well thicken it to a four manifold by crossing with the two ball. So that's like a neighborhood. That's like a little neighborhood of the central fiber back in our diagram there. So you start with that. And now if you have an epimorphism, let's take alpha. If you have an epimorphism to the free group, well, of rank G, I mean, think of this as being represented by a map of the surface to a wedge of G circles. In other words, this epimorphism at the group level, you think of pi1 of the surface as the surface, and you think of the free group of rank G as a wedge of G circles. And that epimorphism is then a map, an onto map. Well, take that map and jiggle it and make it transverse to all the, say, north poles of the circles, assuming the wedge point is the south pole. So make a transverse to the north pole, and you pull back one manifold onto the surface. And that one manifold is a collection of circles. And fill in all of those circles with disks. So just attach disks to all those circles and, well, fatten up the disk a little bit. And then you've got a 3 manifold. One boundary is the surface and the other boundary is a bunch of 2 spheres. And you fill them in with 3 balls, and there's your handle body. So if you think about that, that's just all there is to it. You have a, when you have a map from the surface of genus G to a wedge of G circles, and it's an epimorphism, then you just pull back this one manifold, which are circles, disjoint circles, and fill them all in with disks. And if one of the circles is just a little trivial circle on the surface, when you put a disk in there, then you clearly get a 2 sphere there, which fills in with a 3 ball. And if it's a circle, if it's a real circle on the surface, then you fill it in with a disk, and you got lots of parallel ones maybe, but that's okay. Then you fill them all in, and then the new boundary is the 2 sphere. And so then you fill those in with 3 balls. So that tells you how to get all these handle bodies. All 3 handle bodies come from the 3 alpha, beta, and gamma, those 3 epimorphisms. Okay, now we use the next part. So now just take each of these squares. And so what you've done is taken the surface, sigma G, you filled it in twice with handle bodies. And now you know that the fundamental group by Van Kampen's theorem is the free group of rank K. So what do we know about 3 manifolds whose fundamental group is free of rank K? Hegardt surface of genus G, you get a free group of rank K. Well, now you hit this with a big hammer, you hit it with the geometrization conjecture and conclude that's a connect sum of S1 cross S2s. That's what geometrization gives us. You couldn't prove this before Thurston and Perelman. But you hit it with that, biggest hammer around, and you now find out that that each one of these guys, the 3 manifolds you get by putting together H alpha and H beta, that guy is a connect sum of K copies of S1 cross S2. Well, then you fill it in with S1 cross B3, and there's only one way to do that. That's the old Poincaré, the theorem that you can only add, there's only one interesting way to add fit the fill line S1 cross S2 by S1 cross B3s. So you fill those in, and there's your 4 manifold. So that's the map back. And then a little bit of checking says that each one of these compositions, you go either way, back and forth either way, and it's the identity. So there's the proof. So it really is an easy proof. But what's surprising is that it's true. That's what's surprising. So we just sort of stumbled upon this. It was really, in a sense, this was a tea time theorem. You just ask the question, well, if you apply the fundamental group functor to X, and there's a trisection of a group, can you go the other way? Well, yeah, I just gave you the proof in about 15 minutes. I think it was probably Dave Gay who asked the question. Yeah, so any questions?
You can all,
So I can say,
if you want to ask
can
a
say-
question, you can unmute yourself.
yeah. So I do have some more to say, but let me pause here.
Sorry, Rob, did you say you had more to say?
Yes, I do. I was going to, yeah, I do. I was, wasn't, you know, how it is with mathematicians. They get an audience who's ready to listen when they can't stop sometimes. So, okay, so now the Trisexes people had a Zoom conference, and it was run like the conferences at AIM in San Jose, AIM, that place. And they have a very good idea for conferences, which is that instead of listening to lectures for 5 days, you start out with an hour and talk about problems and list them. And then you ask everybody to, the idea is to get people to break up into groups to work on the problems. And so first step is to say who's interested in the following problem. And people just put down, you can be interested in several different problems. And then after finding that out, it could be that some problems nobody's actually interested in. But then you decide, well, what group do you want to belong to? What problem do you really want to work on? And you break up. And so I ended up in a group. This was a group on trisections and group trisections of surfaces in the force sphere. And so this is group trisections of trisected surfaces in S4. And so this group, the group that started out, so I'll give you their names. There's Sarah. These are all grad students, as it turns out. Sarah Blackwell. And she is currently a student of Dave Gay at Georgia. And alphabetically, okay, then there's me. I'm next alphabetically. And then there's, what's the order here? Vince Longo. And he's a student of Alex Scorpan. Not Alex Scorpan, Alex Zupan. I'm giving you their names because they're going to be in the job market. So Vince is already on the job market. He's a student of Alex Sorpan, and I'll mention the fact that Alex is a student of Maggie Tomova, who's a student of Marty Charlemagne, who was also, besides Dave Gay, a student of mine. And then there's Ben Rupik in Bonn. So he's a student of Arumina Ray in Bonn, who is a student of Tim Cochran, who was a student of mine. And then there's a Mike Klug, who's a student jointly of Peter Teichner and myself. So I didn't know this until partway through this collaboration, that they're all descendants of mine, which I found amusing. So anyway, that's who they are. And Vince is applying, and Mike Klug is applying. And Sarah Blackwell and Ben Rupik will finish a year from now, at least they expect to. So that's the gang. And so what kind of progress have we made? Well, if you take the fundamental group, so our surface is I'm going to call it S, so as not to confuse it with sigma before. So our surface is S, and it's of genus G, and it's a surface embedded in S4. Now, Jeff Meyer and Alex Zupan, they have a series of papers about trisections, geometric trisections of surfaces in the force sphere. And they call these putting the surface in bridge position. And what they do, so here's the kind of picture they typically draw. They draw a line. And this line is meant to be let's say a great circle inside the two sphere. So you have that line, and then they will draw a tangle. I won't make it too complicated, but typically a tangle might have something like this, another one that does that, maybe another one that goes up and.
I'm not sure, Rob, if we can see everything, can we?
Yeah, you're seeing everything.
Yeah, okay.
I'm just drawing this red tangle.
Right.
This, of course, corresponds to an alpha, corresponds to the alpha, one of three. And so this one is, well, there's no point in making this too complicated. It just comes down somewhere. Maybe there's another little one in there. So anyway, they'll draw a tangle like that, and think of this as sitting inside a 3-ball. And then they'll draw another one. I won't draw 3 of them. Then they'll draw another one that looks like goes off in this direction. And, something like this. And they draw this one, and then there'll be a third one, which I won't try to draw. And those are like the 3 slices again. You see the analogy with the 4 manifold. And this is this. And now one property that they want to have is that when you put these 2 tangles together, so 2 tangles together, 2 tangles should be the unlink. So that's what you want to have happen. This is a little bit like saying that when in the 4 manifold case, when you put 2 Haggard surfaces together, you want to get a connect sum of S1 cross S2s. Here you want to get the unlink. So I don't know whether I drew one that gave the unlink. Actually, I think it does. I think that is the unlink, but never mind, it should be. And so you get the unlink in all 3 cases. You put the green tangle in, and you get those unlinks. And that's called putting the surface. So where's the surface? The surface is these 3 links. You put this link and you fill in the unlink with disks, and all those disks together make up the surface. And so they prove that you can do this with any. What did they prove? They prove that you can get this geometric trisection of the surface inside a 4 sphere. So we're doing this in the S4, but they actually do this inside the 4 sphere. And they have a set of moves which will tell you that if you isotope the surface around, then you change these tangles. In other words, they have a nice theory of very much analogous to the 4 manifold case but they do it for surfaces in a four manifold. So you can find their papers. But what they had not done is go to group trisections. In other words, apply the fundamental group functor to the surfaces with respect and deal with the fundamental group of the complement. Just like with knots, it's the fundamental group of the complement, not the knot itself that we want to talk about. Here we want to talk about the fundamental group of the complement of these surfaces in the four sphere, in our case, in the four sphere. And so we haven't written down all the details, but this group, these graduate students, I think that what we've proved is that there's the analogous statement that there's a trisection, so here you have pi 1 of S4 minus the surface of genus G, always a base point lurking around, and you can go over to back and forth to a
You're writing, Rob.
yeah, no, I'm not. Oh, what happened here? You're not.
Not seeing anything you're writing now.
Yeah, but you were seeing it before. Why is this happening? There it is.
Yes, there it is.
I'm writing in the same place that was visible before. Oh, now it's there. Okay. Anyway, that corresponds then to a group trisection of this group, of the same group. Sorry, this is what have I written here? I should have written, it's a group trisection of pi 1, and what I should have written is not pi 1 here. What I should have written is just this, the class of surfaces in the four sphere up to isotopy, that corresponds to group trisections of pi 1 of the complement. In other words, the analogous theorem to what I just said about group trisections of four manifolds. So here you used to have all four manifolds, and that corresponded to group trisections of finitely generated groups. That was the theorem from earlier. And now the generalization here is to do this for the fundamental group of the surfaces of the surface to group trisections of the form of pi 1. So the analogous statement. And I think we're going to be able to prove this.
Is that pi 1 of the surface
Pi 1 of the, not the surface, but the complement.
of the complement?
Yeah, pi 1 of S4 minus SG. Yeah. Plug that in, pi 1 of that. So one thing that's interesting is that there's no characterization of fundamental groups of the surface in the four sphere. And the previous hour, we were just talking about this. I mean, our group was meeting before this talk. And there's interesting questions about that. There's a paper of Gonzalez Acuna and Cameron Gordon and John Simons that is relevant to this. And so, you know, this is not on the tip of my tongue, but there's this stuff, you know, Kerver characterized fundamental groups of surfaces of knots in the n sphere. Going to mention 2 knots in the n sphere. And then, but that doesn't work for the case of 2 and 4. And so there's interesting questions about what these fundamental groups are like. And so we'll probably run into those. And let's see. Well, the other comment I would make is that we're also working on generalizations. We can talk about surfaces in a four manifold, and we have our ideas about that. And there's the case with boundary, where a surface has as boundary a braid running in the braid line in the thickened circle that goes around this two-sphere. And you have a braid in there, and then it bounds a surface. And that can exist inside a four manifold with boundary. And so there's analogies with group trisections. You can take the fundamental group functor on that, and you have a whole picture of group trisections with sub trisections and so on. And does that all pull back to, in other words, a fancy version of what we've been talking about here? And there's some hope for that because, well, what did we need in the previous theorem for four manifolds? We needed that an epimorphism from a surface group to the free group gave you a handle body. Well, here we need that an epimorphism from the two-sphere minus a bunch of points, that's a free group, to a free group, that pulls back a tangle. And, you know, so the pullback, the going from the algebra to the topology, there seems to be a good chance that works because the key theorems, well, the key theorem in the four-dimensional case was the geometrization theorem and the fact that an epimorphism to a wedge of circles pulls back a handle body. Well, the analogy here, this is in lower dimensions, and the analogy here, the key theorems are that if you have a link whose fundamental group is free, then it's the unlink. That's kind of analogous, that's the theorem that's analogous to the geometrization theorem. And so there's hope that this all goes through, but then of course, we're just, this is just speculation. It's our goal of our group, but who knows whether it will succeed. There may be hidden problems. But I think it's likely to work well for the case of just a surface in the four-sphere. So there's 4 minutes left, but I think I've run out. Is there questions?
Yeah. Am I on mute?
Yeah.
No, we hear you.
It's Ken Perko.
Yes, Ken.
Yeah, I was just wondering, this guy D. Gay, is he the undergraduate student of Fox at Princeton 2 years ahead of me?
No,
No,
Dave,
that's a different D. Gay.
Dave is David Gay, and he was a student of mine around 1999, I think,
Oh,
is when he got his PhD. Yeah,
totally different generation.
Totally different generation, yes. Yeah, yeah, you asked this question, I think. Yeah, no, different Dave Gay. Different Dave Gay. Yeah.
It's a common German name.
Right. So Dave Gay is interesting. He was born in Liberia because his parents were sort of missionary types in Liberia, and so that's where he was born.
Wow.
And then he grew up along about from age 8 to 6 to 12 or 14 or something like that, till 14, I guess. He then grew up in Lesotho, this little landlocked country in the middle of South Africa, because his parents were then again well, they were working for AID, and they were working on, international aid and helping out in Lesotho. So that's where he grew up. Then he went to, they sent him back to a private school for high school. Then he went to Harvard, and then he came to Berkeley and got his PhD. But he's an interesting guy. He then took a job in Cape Town after his postdoc, and would have stayed there in Cape Town. I visited him there several times, and he would have stayed there. He liked it there. But he has 3 boys. He got married. He has 3 boys, and they were just too far from grandparents. Grandparents, that was just too far. So they came back to the States. And I think he's one of the stars at Georgia. He's very good. I wrote several papers with him, and he always did it more than half the work. So he's
Why do you call that two-tangle an unlink? It's just one component, isn't it?
in that case, maybe it's one component, but that's still an unlink.
Okay.
Yes. Yeah, I guess I did draw it that way. I didn't intend to draw it that way, but I guess I did. Yeah.
Are there any more questions? I must say, having a co-worker who does more than half the work sounds ideal to me.
I've been lucky that way. I think that's been true of every single one of my co-authors. I'd like to spread that out, because sometimes you work with your students and other people are likely to say, oh, well, his advisor, the famous one, he did all the work. But it's the opposite. All my students, they certainly did the majority of the writing, except for Selman Akbulut, who doesn't write so well. English is not his native language. But they certainly did more of the writing, and I would say they did more of the thinking too. Yeah.
Well, if there's no more questions, then just like to thank Rob for introducing me anyway, to a very interesting topic, and amazing application of the Thurston work.
Incidentally, Selman Akbulut's in town, and he's claiming a proof of that pi naught of the space of diffeomorphisms, the 4-ball, is non-trivial. He's posted it, but it's not understandable. And so he's in town, and I've been talking to him, trying to figure out whether he's got a proof or not. And if I figure out that he does have a proof and that he's correct, I'd be happy to describe that to you in some future date. It has some nice ideas, including swallow follow. Anyway, if that occurs, if he's right, if I understand it, then that's a very nice theorem. Watanabe this fall has got this interesting stuff in which he proves that pi 1 of the diffeomorphisms of the 4-ball is non-trivial, that he couldn't get pi naught. And so to get pi naught is very interesting. So anyway, maybe that'll happen, maybe not.
Well, if it does, I'll hold it to you.
Okay.
Rob.
You're a good audience, so I'm happy to do that.
Yeah. Okay. Well,
Okay.
thanks again, Rob. And next week we have Sergei Gukov.
Yeah, you'll get some algebra.
Yeah, he's going to talk about logarithmic invariance of knots and Q-series invariance of 3 manifolds.
Yeah, well, he's really a physicist, and he's more an algebraist than a geometer, I think. That's my opinion. But interesting, yeah. Well, I'll tune in.
Yeah, in this group of talks, there's been a lot of interaction between topology and physics. So,
Yeah.
yeah.
Yeah. Okay, I'll take off, and that will allow you to.
We
Hey,
can all
Wilson.
take off.
Well, let's see. You have a whole bunch of people I don't know. I haven't been looking at.
Well, we
I
got
haven't been
we had
Uh,
about 24 people at one stage.
yeah, well, there's still a bunch. Hi, Joanna. I didn't know you were in the audience.
How could I miss it? Good to see you.
How could you
Great
miss
talk. Thank you.
Okay. Yeah, no. And I don't know the rest of them, I guess.
These are the unforeseen benefits of the pandemic, that
Yes,
there are all these great talks online one can listen to.
that's true. There's almost getting to be too many.
Mm.
Almost. Yeah. Okay. So I'll say goodbye.
Thank you,
Okay.
Rob.
Okay.
Yeah. Oh, hi, Dale. Okay. So if there are no more questions for Rob, I will end the meeting and see you next week.
Bye-bye.
Right.
Thank you.
Bye. Thank you.
Bye.
Thank you. Bye.